Good night, everyone. So we're starting a new Python Adelaide meeting. So you put the next slide for the agenda. So the agenda for today is, as always, starting at 6. We are 1 minute late. So welcome and housekeeping, and then Owen is gonna speak for about 30 minutes plus 10 minutes questions, all up 40 minutes. And then after that, we'll have some networking until 8 o'clock, and then we have to leave the building because of security. Next slide. So mobile phone on silent or switched off. Emergent exit is on the green sign there. And toilets are this way on the right. Next slide. So that's the sponsor for always, at least since I started being the host, is Agile Insights, where a company that I work for. We are a consulting company that works on the data space, pretty much like data engineering, dashboarding, like analytics, and also, of course, AI now. Next. So these are our expertise that I mentioned. We mainly work with cloud in Azure. We are Microsoft and Databricks partners. Next. So that's an example of a architecture of everything that we connect together to build those analytic solutions. Next. Yeah, I've already mentioned we have got lots of partners, badges that qualify us to provide the consultants in those platforms. Next slide. And here's one of our clients. So I'm based in Adelaide, but the company is from Sydney. We've got clients all over Australia. Next one. And thank you for Patrick, that's been helping me. We are shooting today. Hopefully that video will be in YouTube. Adelaide University that always been good to provide us the room for about 2 years for Agile Analytics, for Insights now. And Owen for speaking tonight, and all for showing up. Without you, we wouldn't have this meeting. So you are important. We need an audience. And that's it for me. I'll pass now for Owen, which is going to talk about I/O in Python. It's going to be a very interesting topic. Usually people say that Python is not a concurrent. There is the GIL and all those problems, but I think hopefully Owen will demystify all those myths and what we can do with Python, concurrency and async programming, parallelism, etc. All right, I'll pass to Owen now. Thank you.
Okay. Oh, thanks, Pedro. My name's Owen, and today I wanted to talk about asynchronous programming in Python. Specifically, I want to talk a bit about the asyncio package in the standard library and how we can use this to more effectively utilize our hardware with our Python code. And I'll apologize in advance. In this, for this first few slides, I'm going to get a little bit anthropomorphic, talking about CPUs as though they could see or perceive things like humans. This is nonsense, but it's just for narrative purposes. My goal initially is to get you to understand the sort of timescales that CPUs operate in relative to the timescales that we operate in. And that will help you appreciate some of the problems that you can run into. So in my attempt to try and help you relate or empathize with the CPU to the extent that that is possible, I want us to compare like how quickly your humans update versus how quickly the CPUs update. So in a manner of speaking, very loosely, we both tick. We have neurons, they fire at a certain frequency periodically. Human neurons, they tick up to about 1 to 200 hertz max. Normally, most of them are ticking much slower most of the time. They don't sustain that speed for very long. CPUs work on very different timescales. They do also have an internal clock signal. So in a manner of speaking, they tick as well, but they're ticking 1 or 2, 3 or 4 gigahertz. So by a very conservative order of magnitude, that's about 10 million times faster than what we tick. And the world looks very different at those sorts of timescales. One way I thought was useful to try and relate to that is I'm sure most of you have seen like high-speed camera footage. You see a 200-speed camera, 300-speed camera, and you can see bullets flying in slow motion, hummingbirds slowly beating their wings. But the way that you might be able to visualize the world from a CPU point of view is if you could record footage with a 10 million speed camera and slow it down consequently by that same factor. With a 10 million speed camera, if you were to record just 100 milliseconds of footage and play it back that much slowed down, it will take you over 10 days to watch the footage. So you can imagine like a common operation, like you scroll your mouse pointer across the screen and click an icon. It might take 300 milliseconds. From the CPU's point of view, in its timescales, a month has gone by and it's watching you move the mouse cursor a pixel every 10 to 20 minutes. If, for example, the user takes a coffee break for 5 minutes, in CPU time, that's awful. 95 years have passed if we were to watch that footage 10 million times slowed down. We won't be alive when the human gets back. So at those sorts of time scales, humans actually move at about the speed grass grows. That's actually like not surprisingly accurate speed ratio. If you look at the speed grass grows relative to the speed it takes a human to move the same distance, it is about 10 million times, give or take a couple of orders of magnitude. And likewise, from human updating thinking to CPU processing, also about 10 million times, give or take a couple of orders of magnitude. So yeah, at our time scales, we're kind of moving like plants relative to them. So I've established CPUs, as I've established, are superhumanly fast. But kind of as a consequence of that speed, they have problems. As I just mentioned, if they're waiting on humans to do something, that is an eternity in their timescales. But even for most electronic communication, loading files, reading from networks, even accessing stuff on your local disk, those are still very slow compared to how fast the CPU operates. How long it has to wait or what that kind of latency is depends on how far the data has to travel to the CPU, which I'll get into in a moment. But yeah, when they're in this state of they're stuck with nothing to do, we call that being input-output bound or IO bound. And that's kind of the problem that I'm trying to show you some tools to tackle in this talk. One kind of slightly, for any of you that are Hitchhiker's Guide of the Galaxy fans, there's this one funny scene that this makes me think of, where the main protagonists in one of the stories, they time travel 37 million years into the future and they leave their somewhat depressed android behind. And then sometime later, 37 million years later, they discover their android Marvin and he's been waiting for them the whole time. And as usual, he's kind of moping about the first 10 million years, they were the worst. And the second 10 million years, they were the worst too, and so on. But I guess the point is, at the timescale CPUs work at, they're all Marvins, they're all waiting, the equivalent of days, months, years, centuries, eons, geologic ages in their timescales for things to happen, because most stuff in the real world and even most electronic data takes an age compared to how quickly they can actually process it once it's made it to them. So one kind of metaphor or analogy, I don't know the original attribution, but I've copied it and slightly tweaked it for these purposes to help you relate to the different latencies that CPUs experience when they're loading data from different sources, is to imagine a CPU as like an office worker sitting at a desk working with stuff. Those of you that have done any like machine code or assembler, you know that CPUs have hardware registers. They're like built or hardware variables. They don't have that many of them, a few dozen of them. They typically store floating or integer numbers, not very many at all, but they're really fast. So you can think of that as like the items on the top of the desk. The thing the CPU is its working memory, the thing it's touching right now with its hands. It's changing these things at like nanosecond time scales. It's adding them together, comparing them, incrementing them, and so on. And then if you imagine with this desk that it has a set of drawers, so CPUs have this cache memory, very fast RAM memory built onto the CPU itself. It's not very big compared to the rest of the RAM memory in your computer, but since it's part of the same chip, it's super fast. And there's different layers of this cache memory, L1, L2, L3, and you can imagine these like the drawers on the desk. So a smaller top drawer that they can pull stuff in and out of, that's L1 cache. L2 cache is a middle-sized drawer, a bit lower down, takes slightly longer to reach into and pull stuff out. And the bottom drawer might be a big filing cabinet drawer, that's like L3 cache. Each of them is slightly slower, but it's still sitting at its chair doing work. It's all very fast still. But most of the time, your code lives when it's executing, it's living in the RAM of your computer. RAM for the CPU to access is much worse again. So now our office worker, they have to get up from their desk, go to the elevator, ride the elevator down several floors, and go to a big filing cabinet room. That's the analogy for RAM. So now we're talking orders of magnitude slower than once the data has made it to the CPU. And they find their file, they go back up the elevator, back to their desk, and they work with it. But RAM is volatile. Your program doesn't start from there initially. It's loaded from a disk. So what's it like to access an SSD drive or a CPU? This is once again getting orders of magnitude slower again. So now our office worker CPU has to get in the elevator, write down, go to the car park, get in the car, drive across town to the local library, pick up a book, drive all the way back to the office, back in the elevator, back to their desk with the book. So orders of magnitude slower again. And worst of all is many of our programs, they're accessing external APIs, they're accessing a database server. Your CPU is talking to a CPU on another computer somewhere. So in this worst case scenario, it's similar to before, like we go back down, get in the car, drive across town, go to the library, we place an interlibrary loan. Then we get back in the car, drive back to the office, go back up, and we wait for several weeks. And then our local library tells us that the book has arrived, back in there, down the elevator, back to the car, drive to the local library, pick up the book, drive back up, you got it at last. This last stage, we're starting at like nanosecond timescales at the top. By the time we get to the bottom, this is like tens of milliseconds, hundreds of milliseconds, whole seconds. It's so slow that even the slowest grass growing meat-brain humans can tell the difference, the delay that they've had to wait. And that's 10 million times worse for the CPU. So why do we care about keeping the CPU waiting? There's a few reasons that might appeal to you. One is like if we're using the hyperscalers, our AWSs, our Azures, quite often we're renting CPUs by time. We're not renting them by utilization. So if they're stuck, blocked, doing nothing useful with the data, waiting for it to arrive, we're still paying for that time and it's coming out of our bank account. That's one really good reason to care. Another reason is like pound for pound, that tiny postage stamp sized sliver of silicon draws a huge amount of power from your computer. You can find funny videos online of people like frying eggs off the heat of their CPU. So, a modern CPU is drawing, like a desktop CPU might be drawing 100 watts, 200 watts. Like if you know the old incandescent lights, you know how bright that is, how hot that gets. They chew up lots of power. And CPUs like globally are consuming a small but significant fraction of the world's total electricity supply. So you might care about that. And definitely a big fraction of that power supply comes from burning, hydrocarbons and stuff. So if you're interested, there's one package called Code Carbon you can check out where it will analyze like the runtime. It's a Python package, you install it, it'll analyze the runtime of your script. And based on which country you're in, it will look at the energy mix of the generators, and it will estimate, how much power did your script just consume, how much CO2 did it just emit. So if you're kind of environmentally conscious, that may influence you. And last of all, for many applications, the value of the output diminishes really fast with the latency. For example, I've worked in a couple of different applications where we do like forecasting, forecasting a flood, forecasting the price of electricity tomorrow. The less far ahead you forecast, the less valuable that forecast becomes, the less time you have to react. and kind of optimize for it. So that's one issue. Certain applications are real-time by nature, driving cars, flying planes, operating, plant equipment in factories. Excessive latency could actually hurt someone or damage equipment. And perhaps more mundane, but even more common, is just user interfaces. An interface with only like 1 or 2 milliseconds of latency is snappy and fast, and we like it. We start getting up to hundreds of milliseconds of latency, then it's annoying and glitchy and slow. So there's quite a few reasons why you might care about the latency of your code. So assuming we do care about this, what can we do to speed up, reduce these IO bound problems? There's a few options. One is you can just buy better hardware. You can buy a better mainboard. You can buy faster RAM. You can buy a faster SSD drive. You can upgrade your internet connection. You have to be careful if you upgrade your CPU, because then you've just made it harder. You have to feed it more data to use it efficiently again, but you will get that bigger L1, L2, L3 caches. Another option, which is very common, especially like with those hyperscaler AWSs and the like, is that you move the CPU closer to the data. If you do need to talk to, query a database, ideally you want your CPU being in the same data center as where the database server is, on some very low latency, high bandwidth connection. So it's not waiting a long time for that data to reach it. And the last option, which I'm going to speak to mainly, this is the kind of the target of using asynchronous IO, is the ability that we can give our CPUs more than one job to do at a time. We can queue up a bunch of jobs such that whenever it is blocked on one of these jobs, it's got something else to pick up. So the common analogy for that is like a waiter in a busy restaurant. They can be taking orders from one table while they wait for the food to be prepared for the first table. And when they're not doing either of those tasks, they might be cleaning some stuff or arranging some stuff. So can have a bunch of different tasks lined up that a CPU can jump between as it's executing. Right, so that brings us to asynchronous programming in Python and async IO. There's a few concepts you have to kind of wrap your head around, but I think it's useful. And there's some lingo that I want to try and get you familiar with that will help you understand what's going on. I mentioned we use the async IO package in the standard library for doing this kind of queuing up a bunch of tasks that our CPU can jump between while it's executing. One of the first sets of, I guess, terminology that I want to get across is this concept of resumable functions. Resumable functions and frames, which I'll explain, but resumable functions is a very old concept. It dates back to some of the earliest programming languages way back in the 1960s. As the technical name is coroutine. So function you can stop, you can leave it, you can come back to it, and it hasn't forgotten its state, and it can pick up where it left off. Like internally in Python, when you execute a function, it has a frame. Your function proceeds through its logic and it exits, and that frame is destroyed. Whereas with resumable functions, there's ways to leave and return to that function and keep that frame intact. The frame basically keeps track of how far through this function has it executed and what sort of variables has the function created locally as it proceeds. There's two types of resumable functions I'm going to talk about in Python. The generators, which is an older technique, and the more recent one, which came in async IO, which is the asynchronous coroutines. Sorry, coroutine is a bit of an overloaded word, but I'll try and disambiguate it for you as we go along. Do have this code in an example. I was thinking of executing it, but I might just speak to it because it's less fiddly. But if you're interested afterwards, there's notebooks for this code where you can go and have a play. I was just going to give super quick, real basic refresher. If you can read this, I hope it's legible, of like how non-resumable functions behave. We can have multiple returns. Having extra returns does nothing. They're not even reachable. And we can call the function. Each time we call this function, it executes from the top, hits the first return, exits. When we enter that function, it creates that frame to keep track of how the function is progressing, what its internal variables are. And when we return from a function, that frame gets destroyed. And another quick revisor, because I think this helps you understand the resumable functions a bit better. Just keep in mind that Python, obviously, functions can return quite complex objects. Functions can return other functions. Yeah, I'm just giving a super simple example of how you can nest a function and return it. But I think that helps you relate to what I talk about next with the generators and the async coroutines, as you can think of them as functions that return functions as well. Well, specifically, they return resumable functions. So if you haven't seen Python generators before, you use the yield keyword instead of return. The moment you put a yield in there, it becomes a generator function. When you call a generator function, you get back a generator instance. It doesn't do anything immediately. It's giving you back the resumable function. And you can't call this resumable function by just with a normal open close bracket notation. That's an error. It's not callable in that way, but there's special built-ins called like the next keyword and a few others where you can call this function resumably, like we call next generator instance. It goes to the first yield, returns that, and returns control back to where we call next from. And you can call next again, go to the next yield, so on, and next, third. If we keep calling next and it runs out of things to yield, it throws a special stop iteration exception. A lot of this stuff actually happens under the hood and you don't think about it much. You don't normally directly call next on these generators. You would typically, if you can read this bottom example, use it with an iterable. So we can just say for I in generator factory, and generator factory returns that generator instance and the iterator calls next, next, next automatically until it gets that stop iteration exception. So that's the kind of normal way you'd use a coroutine. And coroutines have been around, I think, since before Python 3. The very first version of async IO, which I'll talk about in the right hand or left hand side of this slide, is was implemented in much the same way as coroutines. It had a special yield from keyword. It's going back to Python 3.4. And then in Python 3.5, they thought that was too clunky and awkward. So they redesigned it and they added this async and wait keywords. So to create an async coroutine, you typically put an async keyword in front of a function definition. And inside there, you see that await keyword. And semantically, await works a lot like yield does in the generator. This is a resumable function. It means we can exit this resumable function without losing its internal state. And then we can later on resume it from that await keyword or the next instruction after it and continue onwards. Just like with coroutines, the async coroutine function returns a coroutine object. It doesn't directly execute this code. And once again, just like with generators, you can't execute the coroutine object directly. If you try and call it like a function, it's a type error. What you want to do is, well, I guess one way I was trying to illustrate how these coroutines work. Async coroutines are a bit different in that when they await, they don't yield back to the place they were called from, like generators do. They yield to a completely different object called the event loop. And the event loop, which I'm going to describe more in the coming slides, kind of handles scheduling all these async coroutine tasks. It's the one that jumps between them. So it makes it a bit trickier to illustrate how these async coroutines yield to each other. But one simple example I tried to give here is we can create two instances of this coroutine, which you see they do some sleeps, they print some messages, and then we can get the event loop to execute them both. Thing to keep in mind is with async coroutines, this is all running single threaded. Only one thing is actually executing at a time. It's just using this resumable mechanism such that it can execute part of one function, leave it, execute part of another function, return, go back, execute part of the first function again. So this resumable nature of asynchronous coroutines is what lets us bounce between jobs as they become ready to do work. And if you can make out the details at the bottom, when I do asynchronously run both these functions, you can see their outputs get interleaved with each other. It doesn't show the output of the first one first and then the second one. You can see it's the first one is printed and then it yields for this asyncio sleep. And then the next one does its print, it yields for the sleep. And once the event loop has detected that enough sleep time has passed, that the first one can resume again, it goes back to the first instance and so on. So it kind of interleaves. To get onto some of the other keywords and abstractions I mentioned, I don't know how much you're into class diagrams. For those of you that are, this may help you visualize some of the relationships between these types of objects. So in the like asyncio library, we have this awaitable class. I'll mention that this is a slight simplification on the actual details, but largely it is accurate. There is actually like an awaitable interface and coroutine functions, or the coroutine objects that are async coroutine functions return, they implement that awaitable. So anything that can come after that await keyword implements that awaitable interface. There's also other types of futures. Futures are the things that the event loop actually works with. That's what it schedules and jumps between until they're completed. The event loop is basically just a loop that keeps checking each of its futures, giving each one a chance to execute and checking when they're all finished, and then it can complete once they're all done. When you actually use your async coroutines, you wrap them in an object called a task, which is a type of future. There's other types of futures as well. So before you can actually get these async coroutines to run asynchronously, you have to turn them into a task, and then the event loop will schedule them and start running them. When we're doing asynchronous programming, our goal is to we want to await multiple tasks at once. So I'll try and explain some of this code. So in this example, I have a very simple coroutine that just sleeps for 1 second, prints a name. I can await the coroutines directly, like I have in this first block. That doesn't actually speed up anything. When I await a coroutine directly, it just gets added to the parent task. So basically all those coroutines just get executed sequentially, and it will take 5 seconds to run as it goes through each one. If I want to actually speed things up and give the event loop multiple tasks to jump between, so we can parallelize some of this waiting time, I actually have to wrap each of those coroutines in a task, which you can do with that create task function. And once they're all turned into tasks, you can await the task, and this will run much faster. So instead of taking 5 seconds, it'll run in just like 1 second or slightly over, because all that sleep time can be parallelized between the different tasks. And there's some more like syntactic kind of sugar and extra functions that we get from the asyncio library. So for example, we can gather tasks rather than awaiting them sequentially one at a time. Like in this cell, we can just pass all our tasks to this gather function, which will give us back one awaitable object. And that awaitable object will complete once all the things that have been passed to it have completed. So once again, that'll run in about 1 second and you get it back. And the last bit of syntactic sugar that this asyncio gives you, or the gather method gives you, is you don't even have to explicitly wrap your coroutines in tasks. If you pass coroutines to it, they will be implicitly wrapped up in tasks and executed individually, which is handy, but it definitely, for me, it caused me some confusion because it made it harder to distinguish what is the actual thing that makes the coroutines and the tasks different. And you find out sometimes it's not obvious in your mental model why they are different when they seem to behave the same way some of the time, but quite often that is because some of these asyncio functions are automatically wrapping your coroutines in tasks. So I mentioned that we want to start lots of tasks in parallel, and that speeds things up and parallelizes some of the wait time. I skimmed over a bit of the detail though, that the coroutines by themselves, they don't speed anything up. Even if you create thousands of tasks from your coroutines, if you like each in your coroutine, you await another coroutine, so you kind of go down, like calling them recursively. if you just have coroutines and that's all, nothing gets any faster. They just kind of get executed sequentially. The only time that things get truly parallelized is when you await some of these other, I mentioned that there was futures, there's other type of futures from tasks. Some of these futures do fancy things like hook into your operating system callbacks and use low-level APIs that actually come from the asyncio library itself. There's, I guess, the asyncio sleep was a special case one that asyncio manages itself. And then occasionally you might get futures that can wrap up other types of parallelism, like other threads or other processes. So it's only when you use these other types of futures that you can actually parallelize the wait time. I should mention, so most of these sort of tasks are those slow operations, IO-bound operations that I mentioned back in the earlier slides. This is like, if I want to connect to an API or read a local file or run a query on a database server and wait for that result to come back. Those are all the sorts of IO-bound blocking operations that we want to utilize these features for. So in our code, define lots of async coroutines and tasks, but ultimately they have to await something that's not just another coroutine that we define. So where can we get these other features from? Unfortunately, there's a huge ecosystem of packages, and this is by no means comprehensive. This is just a small subset of what's out there. But these are a bunch of packages that integrate with asyncio and connect to different types of data sources. So if I speak to them very quickly, I guess starting with things like HTTPX and AIO HTTP. HTTPX in particular is one I use a lot. It's like an asynchronous version of the requests package that I'm sure many of you have used to pull data in Python. It has both an API that looks exactly like requests, so it has synchronous functions that work pretty much the same as requests, but it also has asynchronous versions. So if you're requesting a web page or something from data from some REST API, while you're awaiting that, your Python script can go off and start doing other things, assuming you've lined up multiple tasks. Or you can just await multiple requests at once. So you can parallelize, if you're requesting 10 different files at the same time, you can kind of parallelize that waiting time while those files are downloading. Top right is like the really popular web framework. So Django was traditionally synchronous. I'm not so familiar with this, but I know they've added async support where they can kind of handle requests coming in from clients. So while they're processing one request, they can start another, or while they're blocked waiting on some IO operation, processing one request, they can take additional requests. And I believe recently also Django ORM, that's their relational database wrapper, is also starting to implement async functionality. So while you're waiting for these slow database queries to go, you can be doing other things at the same time. Court is a fully asynchronous version of Flask. Flask is partly asynchronous at the moment. Like it can't do asynchronous requests, but it can, within one request, it can asynchronously do multiple tasks at the same time. Starlet was one of the earliest web frameworks in Python that was quite popular and asynchronous, and the very famous Fast API is built on top of Starlet. If you're working with relational databases, so moving down to the right side, there's the databases, SQL Alchemy, Async PG or Async Postgres. So you can get these packages to asynchronously query your databases, potentially run multiple queries at the same time, or just progress other tasks while you're waiting on these queries to come back to you. Bottom right corner, AIO files. As I said, even reading local files off your disk is slow compared to what the CPU can do. So AIO files gives you a way to await a file being read. AIO Boto3 is like the asynchronous version of the AWS Boto3 package. So almost all the things you can do with AWS services synchronously, you can also do asynchronously with AIO Boto3. UV loop and win loop are slightly different type of things. So as I showed you in the previous slide, CPython has that event loop but the event loop is actually pluggable. Asyncio gives you a reference kind of implementation event loop, which is nice to debug. It's not the fastest to run and fastest to do this sort of task juggling. So for most people working on Linux or macOS operating systems, you use UV loop, which is a much more highly optimized event loop that you can plug in. Kind of sucked to be on Windows for quite a long time because it doesn't work there, and there wasn't. But more recently, it's a newish package, but there's also WinLoop, which is like the Windows, what do you call it? It's like a fork of UV loop that implements what works around the limitations that UV loop has that constrain it to only working on those POSIX operating systems. So yeah, it's highly recommended if you're writing production asynchronous code that you would be using one of these event loops and not the one that comes by default in asyncio. Hishul and AIO cache are just asynchronous versions of caching libraries and decorators. Hishul works with HTTPX, so you can cache your REST API requests. And if you're making the same request multiple times, it'll just give you back the cached version. AIO cache is more like a general cache decorator that you can stick onto any async coroutine. Bottom left have some of the popular testing frameworks. So if you want to test async coroutines in PyTest anyway, you can use the PyTest HTTP. To get that right. PyTest asyncio package. And there's also PyTest kind of fixtures, other packages like RESPX, which is like the async version of the responses package for mocking requests, and PyTest HTTPX is the similar deal. On the left side, just touching quickly, these are like your document or key value database asynchronous things. I haven't used Couchbase. Redis used to have separate versions of packages for doing the async queries, but its async versions have recently been incorporated or consolidated into the main Redis client. Motor is the MongoDB asynchronous client, if you're querying that. And working right back to the top, once again, asyncio and NAIO are quite different. They're not about connecting to other data sources. NAIO is like a more advanced async where you can do really sophisticated kind of hierarchical awaiting. Like if you have one task that wants to await 10 other tasks, and based on whether one of those 10 subtasks fails, you want to have some different behavior in the top level task, doesn't want to retry, doesn't want to fail the top level task. It gives you fancier abstractions for working with kind of this awaitable asynchronous operations. And Asyncio is a very small package made by Sebastian Ramirez. He's the Fast API creator. He does a lot of cool stuff with asynchronous code. Asynchronous just gives you some nice kind of like syntactic sugar decorators to make it easier to mix asynchronous code with synchronous code. One issue you run into with async code is it's very easy to create accidental denial of service attacks because you can do so much stuff at once. You can try. Most computers do not like opening 10,000 files concurrently at once. Definitely most APIs don't like getting hit with 10,000 concurrent requests. Yeah, if you use it naively, you can kind of really mess things up. So I guess going on with that, a bit of a Spider-Man theme. This is a minor superpower and you should use it responsibly. These packages I just mentioned, it's super easy to like web crawl hundreds of pages simultaneously. You could scrape a whole bunch of Wikipedia pages much faster than you could synchronously. But yeah, please show some restraint. Don't smash it as hard as you can with these. And to that end, there are packages, well, there's some functionality built into asyncio itself, like this semaphore where you can limit how many subtasks one parent task can spawn at once. If you're using something like that HTTPX to do like REST API requests, it does have configurable values in it to limit how many things it can do concurrently. And there's other packages like this AIO limiter which also, as the name suggests, it will like let you kind of rate limit some of your asynchronous operations, so you can control how many tasks can spawn at once. I guess we're time. I can probably potentially jump out and show you one code example. I guess I'll run it first. In this code example, I'll jump back to the code in a moment. In this code example, I was showing off that some of the asynchronous file reads, where I just write an arbitrary number of files and then I read their contents as quickly as possible from the disk. And yeah, the input is not very exciting to look at. I'll show you the code where we just control how many files we write and the size of them. And depending on how big they get and how many they are, asynchronous can give us more or less of a speed up. In this case, it's giving us almost like a 6x speed up and how quickly we can read files from our local disk. There is kind of trade-offs and overheads. If we're only reading very few files and those files are very small, they will actually read faster synchronously, because starting up that event loop and doing all that context switching between these resumable functions does add a small amount of overhead. If there's not much waiting time actually happening to parallelize between, running these asynchronous tasks might not give you any speed up. But once you start to get lots of tasks and the wait times become more significant, in this case, if you make the file sizes bigger, then it doesn't take very much before like the advantages of running things asynchronously outweigh the kind of the overheads that it introduces once you get enough wait times that you can parallelize at the same time. But yeah, this will all be in a GitHub repo that I'll give you a link to at the end of this if you're interested, but you can kind of look at the example code of how I create some files and yeah, I think the main gist is that we have like a simple synchronous file reader and we have an async version. In this case, the async version is almost identical to the synchronous version because we're using the asynchronous version of the pathlib paths that standard library gives you. So any IO gives you its version of a pathlib path for accessing files, which is asynchronous, and you can read the file contents from that. And yeah, I said you can read the the contents from multiple files at once, and the delay can kind of be parallelized, so you can get that content much quicker. Don't expect you to read all of this content, but I'm just gonna very quick kind of history that asynchronous programming and async IO is one of the fastest evolving parts of the Python ecosystem. So the original version of async IO was introduced over 10 years ago, back in Python 3.4. Those async and await keywords came in 3.5. If you're interested, I think Python C# was the first popular language. Async and await is common keywords in lots of programming languages. I think C# was the first one, the first popular language to do it. And since then, many other programming languages have copied this paradigm of async and awaitable functions. Python was one of the first languages to copy C#, I think, but lots of them were planning it at the same time. JavaScript introduced its version of async and await roughly the same time, maybe slightly later than what Python did. Many of these are just small quality of life improvements for developers over time. I think some of the main points of interest were like 3.11 when we got task groups and exception groups. Before that, we didn't have any good ways of handling exceptions being raised from asynchronous tasks if you have like 10 tasks going at once. Whereas these task groups gave you a way to handle receiving exceptions from multiple tasks at the same time and being able to inspect each exception. Guess there've been other performance improvements, and even in the upcoming Python 3.14, they're still making changes. Right, one of the most interesting features coming up in 3.14 is some new tooling to inspect tasks. At the moment, it's very hard to see in Python 3.13 and before, it was very hard to keep track of how many tasks were being running at once or being awaited at once. In 3.14, there's new tooling where you can actually connect to a running Python interpreter, and you have different ways to query. You can see what tasks are being awaited at present, and much better inspection tools. So that's kind of an interesting thing that's coming up. Almost at the end. If you're interested in learning more about async programming, there's a few people and I guess their content that I do recommend following. I mentioned Sebastian Ramirez, who is famous for creating Fast API, and he also created this async library. If you ever check out the documentation on any of his projects, his documentation is always fantastic. And he even breaks out some simple async tutorials as primers in the Fast API documentation. And if you look at his async package, it also gives kind of good introductions, and it just, it has some nice developer quality of life improvements to make using async coroutines easier. There's Lucas Schlanger. He's the developer in residence for C Python. He was the release manager for some of the earlier versions of C Python. He's given many presentations on asynchronous programming. He does a podcast now called Core.py with Pablo Galindo, another one of the core developers for C Python. And they spend a lot of time talking about new async features that are coming up that they've both worked on and that. So if you're interested in finding out, what's actually happening in C Python and what's currently being developed, that's a really good podcast I recommend. For learning about asynchronous programming and other types of concurrency, a really good course I tried was from Michael Kennedy. He's also a really prolific podcaster. He has several Python podcasts that are the most popular Python podcasts, and he also does training courses. They're not free, but sometimes you can find them very heavily discounted on Humble Bundle, and that's where I first learned a lot about doing asyncio programming. And I guess last of all, if you want a different take, if everything I've said sounds a bit like asyncio, rah, 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 it's fantastic. Not everyone likes it. You might be interested to look at some of Armin, I'm not sure how to pronounce his surname, Ronica. He was one of the original developers of Flask. He worked at Sentry for a long time. I mean, definitely cares a lot about concurrency and using CPUs efficiently, but he just doesn't particularly like the abstractions that asyncio has. And there are a few kind of issues with it that I might touch on very briefly, although I'm not aiming to go into them. But if you're interested in a more critical view of it, you might want to check out some of his work. He is a pretty prolific writer. He has a very extensive blog and does lots of posts on different platforms. I guess I should try and scope out what we covered. So my aim today was just to introduce you to asynchronous programming concepts, hopefully help you remember some of the lingo, show you some of the packages and the actual IO bound sort of problems that we try and tackle with it. There's lots of things I've left out that you might want to dive into yourself more in future, or potentially other topic for future meetups. So I didn't talk about some of the more advanced async. Like if you wanted to write your own async package, like some of those ones that I showed off, how do you write these other types of futures that can do things truly, that can parallelize wait times? I haven't covered that, but you can look into that. There are special dunder methods in Python, like there's a dunder await and a few others that are asynchronous specific. I didn't talk about those asyncio kind of primitive functions that hook into the operating system, which are the key ways that many of the asyncio coroutines give you these speed ups, because they can kind of offload some of the waiting work to the operating system to be notified when is a file handle ready to be read from, or when is a network connection open. I kind of skimmed over the event loop. There's different ways you can create this event loop. Many of my examples, I should have pointed out, come from Jupyter, and Jupyter does some of the setup for you. Like you didn't have to see me create the event loop in some of those examples, but in your regular Python scripts, you do have to do that. You can't just start awaiting coroutines or tasks from any particular place. You need to explicitly start this event loop and normally give it one coroutine to start with that it will turn into a task, and that thereafter become the parent task for all other things that event loop runs. There's challenges with asynchronous programming. Like, it's just one thing is it's just more code. Often, yeah, your async code gets more complex. And like with any sort of concurrency, it becomes way harder to debug, because then it adds a timing aspect to your program. Based on how long the delays happen, your programs can they will no longer execute in deterministic orders. Depending on how long it waits to open a file or waits to get back a database request, the order that these coroutines end up executing in will be different. And that adds a whole new dimension of complexity in terms of understanding and reasoning about your code, which is, I guess, why some of these new inspection tools might help with that. I mentioned about the ways you can accidentally create denial of service attacks by smashing APIs too hard. It can still be a challenge. There are tools that I showed you to try and limit that, but it's hard to implement things like back pressure if you are hitting a resource too hard. If you have multiple like coroutines or third-party packages especially that are talking to the same resource, it's really hard to rate limit them all together, especially if you don't control them directly. If you only say want to allow 5 concurrent requests to go to your remote database, but in multiple parts of your code, you're making asynchronous requests to it, it can get quite complicated and challenging to manage these rate limits yourself. And I guess the last thing is, yeah, async doesn't mix well with most of the normal dunder methods. You can't await coroutines in any of the normal synchronous dunder methods. You especially can't await them in like your dunder init and your, is it dunder delete, your like cleanup ones. So you can't tie asynchronous operations to the lifetime of regular Python objects, which is some of the limitations I've run into with it particularly. Because other things I mentioned is that these concepts of asynchronous programming, they predate the asyncio library in Python. There was other Python libraries doing asynchronous programming with slightly different abstractions before asyncio existed. Some of these libraries or applications still exist today. It's Twisted, I don't know much about. Tornado is like an asynchronous web server. It's still used in Jupyter to this day. G-Event, not so familiar with. Trio is another one like the AnyIO. It kind of even pioneered some of the concepts that asyncio ended up adopting, but it, like that AnyIO, Trio has much more advanced asynchronous abstractions from creating complex relationships between parent and child tasks and how you might want them to interact with each other. There's other types of problems you have with CPU. There's CPU bound problems where one of the cores on your computer might be maxed out, processing data really fast, and the other 15 cores are doing nothing. asyncio doesn't help with that, and that's kind of a completely different topic if you want to get into how do you parallelize work across multiple CPU cores. And I mentioned there's a number of other packages you can check out if you have that CPU bound problem instead, where you can either parallelize work to more of the CPU cores on your own computer, or if you have really huge jobs and you want to rope in CPUs on other computers or a whole cluster of computers, you can check out things like Dask or Apache Spark that will let you kind of farm out jobs to lots of CPUs all at the same time. But that's more relevant for these CPU bound problems, not the IO bound problems that I've been talking about. And that's pretty much it. If you're interested in geeking out about any of this stuff, my contacts are, there's the repo up here with all the examples, and I'll put a copy of these slides in there as well if you're interested in. And that's it. If you have any questions or comments, yeah, please hit me. Otherwise, thank you very much for your time.
The asyncio is basically single threaded.
Yeah, that's the nature of asynchronous programming, that there is parallelism happening, but at a different level of abstraction. But in your Python code, only one thing is actually executing at a time. Yeah, there might be some exceptions where you can use async coroutines to wrap threads or processes, so they can something can run concurrently in a thread or process that's wrapped by an async coroutine. And when that process or thread finishes, it kind of marks that feature as done and then async. But for the most part, no real parallelism happens in your Python code.
Yeah.
It's handled at a lower level, usually by the operating system, and it's kind of callbacks and events. Yes.
When you look at code you're working on, how do you identify pieces of work that would be good candidates to make asynchronous?
I think that kind of relates back to what I was trying to cover way back at the beginning when I talk about the delays of CPUs accessing data. There's just operations that we know, like those bottom tiers of that analogy with the office worker and that, anything like reading files, definitely making requests to external databases or connections to external APIs. You absolutely want to do that asynchronously if you're doing any volume of that work concurrently. Yeah, definitely that cross-computer communication is times where you're going to be potentially IO bound for a long time. Yeah, as I said, the tens of milliseconds, hundreds of milliseconds, whole seconds. Database queries could run for minutes. So that's the sort of thing I look for, that are just kind of fairly obvious IO bound operations that I would want to try and parallelize. But yeah, once again, it only works if there are actual other tasks that you can do at the same time. If you're kind of just doing one task sequentially and everything depends on the previous state or the previous steps, it's pretty hard to make that asynchronous. Sorry, yeah, question.
Yeah, thanks, Al. I'm just wondering, is it possible to run into traditional parallelism issues, deadlocks, race conditions, that sort of stuff?
That's a great question. Short answer, yes, but it doesn't happen as much as it would with, say, multi-threading. So the great thing about asyncio is the control only jumps between these tasks when you hit those await points. So while you're running code from one await to the next, nothing else can be happening in any other task. So you don't have to worry about any sort of race conditions in those blocks. So it's quite rare. Often I don't worry about race conditions at all. Occasionally, depending on how you design your async coroutines, you could have race conditions where they kind of persistently use some resource for some amount of time. There are the same sort of mutaxi locks in asyncio as well. Well, asyncio has its own versions of those things if we need to control access to to deal with those sorts of race condition issues. Oh yeah, sorry.
Is there any situation where you think it would be better to use a generator over async?
I absolutely do still use generators. I guess that classic case where you want something that works with an iterable, or you want to treat an object like it is an iterable. And I guess the other case where you very commonly use generators that's nothing to do with iterables is as the shorthand version of generators used for creating context managers. So if you're familiar with context managers, there's like an entry, and when you use the generator version of a context manager, so it'll have just like one yield. It'll do something when you enter the context yield, and then runs all the code in your context, and then it returns back to that generator to do any cleanup. So if you're using context managers to access some resource where you want to establish a connection and close it or clean it up after it's done, it's really common to use generator. There's other ways to write context managers with a class and a dunder enter and a dunder exit method, but it's much easier to write a context manager as a generator. Yeah, generators, typically iterators, context managers. You can do really fancy things with generators where you can pass them extra information while they're doing that resumable run. So you can nest them or use them in quite complex ways, which is kind of what they did do for that first version of async IO. But I think that the syntax was just quite clunky, and that I guess what async IO gives you is that event loop that handles all the scheduling for you. You could do the same thing with generators, but you would have to kind of implement all that kind of scheduling logic yourself. Yeah, hope that answers some of your question. Yes.
Is there any situation that it would be a disadvantage to use asyncio or generator?
There's definitely times where you're doing small, fast things where it just doesn't make sense to use them. Like there's no performance advantage to using them, and you probably don't want to use them because they add extra lines of code to your code that you have to maintain. They have those properties that make it harder to reason about the code. So there's kind of an extra kind of technical burden or maintenance debt that you're putting on your developers. So I definitely wouldn't use them if there was no performance advantage, well, especially with asyncio. If there's no opportunity to parallelize wait times, I wouldn't be using them because it makes your code harder to debug and reason about. But generators, they're almost ubiquitous. We use them a lot, but it kind of just, that's more like just it's more like just whether they're syntactically better, whether they express the logic of your code better, and which is a bit of a subjective judgment, I guess.
The asyncio run function that you showed sometimes is the entry point for the event loop to start.
Yeah, that was a kind of a syntactic improvement that came in slightly later versions of Python. I guess that was another thing I neglected to mention. As I said, asyncio evolves a lot across versions of Python, so you have to be kind of quite conscious if you're using an older version of Python. Certain things you have to be more there's certain patterns that might get better in later, but if you're using a more recent version of Python, so you have to be quite conscious of what's available in your version of Python. That asyncio run was introduced relatively, I think it was like 3.7, but it was nice in that you could pass asyncio run a single coroutine, it would wrap it in a task, and it would create the event loop for you and have the event loop run that like top level task. So it like tied the lifetime of the event loop to the lifetime of your initial coroutine that you passed to it. Whereas I think in earlier versions of Python, and you can still do this if you want to, you can instantiate the event loop separately. You don't have to have any task to create an event loop. And then you can assign tasks to an event loop you've already created. But yeah, there's some funky rules about what you can do when you can instantiate. So you can create as many event loops as you want in one thread, but only one event loop is allowed to run at a time in that thread. The others have to be idle. And if you create code, like if you create tasks for one event loop, say in one thread, they're bound to that event loop. They can't be shared with other event loops. That makes sense. But yeah, sorry, I don't know if there was more to your question than just the run.
Yeah, just one more thing. So the run function itself is synchronous. Like
yeah, exactly. You always have to have a synchronous starting point to start this event loop. That's a very good observation. And you saw when I don't know if I can jump back to that slide quickly. This is the one you're referring to. So I have like an async def coroutine, but you see I'm not awaiting it. We're still in like synchronous world here. I just want to, when I call that async coroutine, you remember that I get back a coroutine object, and it's that coroutine object I want to pass to this one method, and then it will create the event loop, and it will wrap that initial coroutine object in a task and start off the whole scheduling. Once that task is running, there's always, usually if you're doing anything asynchronously, you're always doing it within the context of a task, but that task is free to spawn as many other subtasks as it wants to.
So if the current task completes, then my code moves to the next line, it will run.
Yeah, I guess in this case, if you were doing something, if you create 2 task objects in this first task, you can await. The moment you create those task objects, they're scheduled and they're going. At some point, you should await them. You always want to await all of these tasks, but you're free to create them earlier and await them later, which I think I kind of showed in one of those earlier Jupyter Notebook examples where I create the 5 tasks and then sometime later I await them one at a time. You will get errors if you ever create a task or a coroutine and you don't await it at some point. Yeah, Python will whinge at you for doing that.
I guess on that topic then, typically your program will have one call to asyncio.run, which then
Yes.
triggers off all the other processing.
Yes, exactly. Yeah, so that's why everything kind of happens within the context of if the event loop is doing anything, it's doing it within the context of a task. Yeah, if you want, it's probably not a great, usually in all my async programs, I just will do that run command just the once, and normally the lifetime of that task is pretty much the lifetime of the application. It doesn't die, but you can create an event loop anywhere. You still have to obey that rule that you can only start one per thread. Like you have to stop one before you can start a different one. But yeah, you could create as many event loops as you want, and wherever you want, and they could be as short-lived as you want as well. I think it's if the event loop itself, I think, goes out of scope and it gets like garbage collected and deleted. Yeah, if there's still anything that hasn't been awaited, I think that's what triggers it to get angry at you and whinge that you haven't awaited something. Yeah. Oh, sorry.
Are there any common patterns for error handling? Like
Error
JavaScript, you get a promise object type and sort of like do something with go error, like get a message or whatever.
Yeah, a promise and a future are, but like semantically they're kind of the same thing. You can catch exceptions from your tasks in just like they were a normal function, like you can wrap a try catch block around and wait call, and if that task that was spawned coroutine that's running throws an exception, you can catch it at that point. As I mentioned, there were issues like if you spawned a bunch of tasks and a couple of them threw exceptions at the same time, the old behavior was that you'd only get the very first exception that came out, and that would like kill everything else automatically. Whereas with those is it task and exception groups, it does give you a mechanism where you can catch multiple exceptions from tasks at once. I think the behavior is it still kills them all. And I think with like that asyncio, I think it's with the gather operation, it does take some extra arguments from memory. So either gather will return the results of all the like coroutines or tasks that you pass to it. But with some other arguments, if any of those tasks raise an exception, instead of getting back the return value for them, you can tell gather to give you back the exception that they threw in that place instead. But short answer is, yeah, beyond that, I don't know if there's any really good. I do know that some of those other packages like NEIO and the Trio that I mentioned, that asyncio copied a lot of the ideas from, they do have more advanced patterns for dealing with exceptions happening at different layers. They have like concepts of nurseries of child tasks and different ways that you can respond if something goes wrong with one of those child tasks. But I'm not so familiar. I haven't tried using Trio or NEIO for doing anything more advanced like that. I think, but yeah, I have used the gather call where I have it return exceptions, and yeah, then I just kind of iterate over the whatever gather gives back to me. Check, is it the return type? That means it succeeded, or have I got back an exception type? And then at least I have some options to like retry that particular task that I'm doing through the exception. I think the gather has the advantage that if you tell it to collect those exceptions, it'll try and run all the tasks. So even if one throws an exception, the others will keep on going. And once it completes, you'll either get back all their results or the exceptions. Whereas when you use those exception groups, you might get some concurrent exceptions that happen really close together, but I think by default they will kill the other tasks. So you will only get back the ones that happen to throw exceptions like almost concurrently. That makes sense. All right, that's it. Thank you very much.
That's it.
Yeah, you can join now from pizza and then Owen, are you sticking around?
Yeah,
And
a little
then
while.
you can continue to ask questions and call. No problem. All right, thank you.
See.